Okay, so continuing on with our review set 12A, we're now starting from question 6. Part A says 8 to the power of 2/3. So using our index rules, we know that means the cube root of 8 squared, which is the cube root of 64. Now, that's a pretty good answer, but you should be able to then go to that 64 is 4 cubed. So the cube root of 64 is 4. Now looking at part B, we have 27 to the minus 2/3. So the minus means we know we're going to be 1 over. And we're 1 over 27 squared cube rooted. Because remember that the number on the top is the power we put it to. The number on the bottom is the cube root. Now, one thing we might recognize here is that 27 is actually 3 cubed squared. So by cube rooting 3 cubed, we end up with 1 over 3 squared and 1 over 9. Okay, looking now at question 7, solving for x. So this is where we need to be able to put any number we see, such as 32 here, to the base number given on the left-hand side of our equation. So we have 2 to the power of x minus 3 is equal to 1 over 2 to the power of, and you can go through your powers of 2 to get 2 to the power of 5. Now 1 over 2 to the power of 5 is the same as 2 to the power of minus 5. And once we have them both at the same base numbers, now it is possible to equate the powers. So by equating the powers, we now have x minus 3 equals minus 5. And then we add 3 to both sides. So we solve it as x equals minus 2. Okay, for part B here, we have 9 to the power of x and 27 to the power of 2 minus 2x. Now we can't equate 27 as a power of 9, but we can identify that both of these can be written as 3 is the base number. So what we have here is 3 squared to the power of x is equal to 3 cubed to the power of 2 minus 2x. Now, we know from our index laws that when we have a power to a power, we multiply. So we can say that 2 times x, or 2x, is equal to 3 multiplied by 2 minus 2x, or 6 take 6x. So if we now add 6x to both sides of our equation, so that it cancels out the minus 6x on that side, we get 8x is equal to 6. X is equals to 6 divided by 8. Or 3 on 4. Now here in part C, we haven't actually done these natural base powers, but they work exactly the same as any other base. So if we have e to the power of 2x is equal to 1 over e to the power of a half is equal to e to the minus a half, we end up with 2x equals minus a half, x equals minus 1. Oops, sorry. So divide both sides by 2. It's minus 1 on 4. Okay, for question 9. We have here the graph of y equals 3 to the power of x. So it's an exponential relationship. And the questions are asking us to read some information off the graph. So first of all, what is 3 to the power of 0.7? So that's saying, well, what happens when x equals 0.7? So we come over to our graph. Where x equals 0.7, so x is equal to 1 here, so 0.7 is here. We read up on the graph and across. So here's 1, 2. This would be about 2.2 at this point. So we can say where x equals 7, y is around about, because we're reading enough for graph, we're not too precise, 2.2. Same thing for where x equals minus 0.5. So here's 1 again, so we count x equals minus 0.5 up to this line and across. We have 0.2, 0.4, around about 0.6 there. Y is around about 0.6. And we can find the value of x where we're given 3 to the power of x equals 5 in the same way. So we just read off this time, instead of reading off the x-axis, we're going to read off the y-axis. So I might use purple pen. Okay, so 3 to the power of x equals 5. So 5 is this point on our graph. So we can measure it all the way across. And then all the way down, trying to be as precise as possible. We have 1.1, 0.2, 0.3, 0.4. So around about 1.45. So we can give the x value as round about 1.45, where 3 to the power of x equals 1/2. On our graph again, we just read it off. 0.5 is round about here. We go across and down, minus 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So it's around about minus 0.6. Now, for 6 times 3 to the power of x equals 20, we have to do a little bit of algebra first. So if 6 times 3 to the power of x equals 20, then for 3 to the power of x equals 20 on 6, and that is around about 3 1/3. So on our graph again, we can look for 3 1/3. One, 2, 3. 2.4, so it's round about in between these two. Straight across to our graph and measure it down here, and we get around about 1.1. So we can solve it there. X is approximately equal to 1.1, where 6 times 3 to the x equals 20. Okay, now we have question 12, the final question for this revision. And we have the temperature of a dish that is cooling down. And so the temperature of the dish is given by T as the subject of the time is equal to 80 times 0.913 to the power of T, where T is the time in minutes. Now, straight away we can see that 0.913 is less than 1, so this is a decay problem. It's going to be going down. And we can start looking at our questions keeping that in mind. The initial temperature of the dish is the temperature at time equals 0, and that's equal to 80 times 0.913 to the power of 0, which is equal to 80 degrees Celsius. Remember those units. So finding the temperature after 12 minutes. So temperature after 12 minutes is equal to 80 times 0.913 to the power of 12. And if we put that into our calculator, we can round it off to get approximately 26.8 degrees Celsius. Now, if you're putting that into your calculator and not getting that result, please see me and make sure that you're using your calculator correctly. Very similarly, very quickly, T at 24 equals 0.913 to the power of 24, approximately 9.00 degrees Celsius, and the temperature after 36 minutes approximately equal to 3.02 degrees Celsius. So those are all just a matter of plugging them into your calculator and making sure that you're getting the right results. Now you're asked to draw the graph here. We've been through that a lot in class, so I'm not going to do that here. I might enter one later so it's in your work solutions. But remember, at a minimum, you need to have your axes labeled and a scale, and those 1, 2, 3, and 4 points all labeled on your graph. Now this says, hence find the time taken for the temperature of the dish to fall below 25 degrees Celsius. Now I've got the graph somewhere else. I've put into my Desmos, and I can read off the graph that to get below 25 degrees Celsius takes approximately 12.8 minutes. Now, depending whether or not you've used a calculator to draw the graph or you've drawn it yourself, the accuracy of this result may change. But as long as I can see from the graph that you've drawn that you've read that result off the graph, then that's fine. Okay, so that's the end of the review set 12A.